This video is about lambda. What is lambda? Well, lambda is the constant of separation. Now, what did we separate? We separated the radial from the angular. And what we want to do is figure out what's inside this lambda, because you've seen some things about L's and M's that are in there, and there wasn't really much explanation for it. So that's where we're headed on this one. 1 over r plus 1 over y. Does that look familiar at all? This is the r, y, the two separated parts. And when we did this manipulation, the 1 over y is an angular function y. This is the radial function r. Same thing that's shown up here. And there's a 1 over r that occurs. And then we have a function that is a function of r. Well, that's no big surprise. And we have a function over here, which is a function of theta and phi. Okay, no big surprise there. No revelation yet. Then we're going to make up two other functions. A function of r that is this thing. So again, we're just creating two brand new functions to make a point, and that is these two added together equals a constant. Now that forces these two to be constant, because if this isn't a constant, then changing stuff over here, it shouldn't change that. So this has to be a constant. If this isn't a constant, then changing stuff over here shouldn't have any effect on it. So those two have to be constant. Okay, if you dare. This is what we just covered there, only I drew it, so of course it's more beautiful. Since we said that each of these two things had to be constants, let's look at what I did here. I said 1 over y, which is the angular function. Here's the angular function. Here is the negative lambda. That's what we want to know, is the lambda. And we're saying that that's the constant. And down here we're saying the radial term is a little different. It's just the lambda plus, well, what's the energy terms? Well, the energy terms are the energy eigenvalue and the potential energy. So those are the energy terms. And those are constant in one particular environment. So that constant means these are a constant, that's a constant, everybody's happy, so that it's all works out. Now this lambda, we're not going to find out what's inside the lambda yet, but we just want to prove out how this is all going to occur. This should look familiar to you. Here's the angular momentum operator over negative h bar squared, because that's in front of the L, so we got to put negative h bar squared down here. And that's equal to y, to lambda. So let's see, if I just move terms around a little bit, then we've got, that looks like a Schrodinger equation, and that we have the operator on the function. We get a constant times the function. So that's the Schrodinger way. That one was quick. That one was nice and easy. Sorry, it's not so easy here, because look at all this stuff. Well, the radial function is a mess, and I had to struggle over it quite a bit to try to get things straight in my head, so hopefully you can follow along. Here's the radial function. That doesn't look too bad. First partial of r squared times partial of r with respect to r. There's the with respect to lowercase r. Here's the lambda, and here's the energy terms that I promised you. Here's the energy r squared. Energy squared with r in the numerator. That's not right. It's not supposed to be there. Well, things will work out. Don't worry, we're not done yet. And then the 2m over h bar squared. Why did that occur? Well, that's because the h bar squared would normally be over here. Anyway, just wait. I'll help you figure it out. Just take your time and we'll do it right. Okay, let's just take this and say that we're going to start expanding this. Now, when it's a product of a derivative, you have to take one thing times the derivative of the other plus, and then you interchange them. So here we're taking the first derivative of r with respect to r, which hasn't happened yet, and we're taking the derivative of r squared, which is 2r, plus, and we take the r squared times the derivative of first derivative, which gives us second derivative. Well, that wasn't too bad, was it? Now, here's the lambda, and none of this stuff changed. So, why does it get complicated? Well, let's go back and multiply times h bar squared over 2m, negative h bar squared over 2m. Now, where did that come from? Well, that comes from the energy. This is the energy Hamiltonian portion of the, this is kind of like the kinetic energy type of thing, and that really goes out front. Anyway, trust me. I'm sure you trust me. Right. Okay, let's keep going on here. Now we take 1 over r. What did we do? Did we do anything different? Oh, what happened here? What? This went from 2r to 2 over r. What did we do? Oh, we divided the whole thing by r squared. That'll get rid of the r squared by the e. So I divided everything by r squared. So 2 over r divided by r squared, do the quick cancellation in your head, you get 2 over r. Plus r squared disappeared over here. So see, we're simplifying some stuff. And the negative h bar squared went by the lambda. See, there's the lambda. And we divided by r squared here. The e r squared, just left e all by itself. And now the potential energy looks right because the radius is in the denominator. Okay, if you dare, I will continue to simplify and magnify and confusify. Here's negative h bar squared. And what did I do next? What did I do next? Oh, I kind of reorganized stuff. I put the second partial of r with respect to r squared over here, and then the 2 over r, first partial of r with respect to r, plus, oh, I brought this over from the right-hand side. It became a plus h squared lambda over 2mr squared. And this is the potential energy, and it should have a negative sign in front of it. So that all looks good. And here's r. So this is kind of a Schrödinger thing, but it's kind of messy. We want to clean it up. We want to come to some nice, neat form. So I'm going to look this over and see if I changed anything. Oh, well, I brought the h bar squared over 2m inside this parentheses, so it makes this look a little easier. Just got the lambda over r squared times r, and here's the potential energy sitting out there, ER. Well, you might say, well, we're done. That's close enough. But here's what we don't like. We don't like this first partial derivative, or it's not a partial, it's all in one radius, only one variable here, so we don't need partials. But what's going on here? Well, I'd like to get rid of this. Now, who would have thought there was a way to get rid of this? What we're going to do is a little trick. And it's a trick that I didn't discover. No way, no way, no way. Somebody else discovered it. That we can simplify this thing to make it look a little bit more physical sized or physicist sized. And I'm going to take it, develop a new function called u over r, u of r over r. And I'm going to replace all the r's of r with this u function over r. So let's go to the next page. Oh, got to reduce my picture here so I can see the screen. There, I think all the characters are visible. This top line's no different. Top line is no different. That's what we did before. And to keep things clear, I put this little guy right here and I put a red line under it. And this one I put a green line under it. And the red line is going to be developed in all of these lines here. So this is the red line. So we're just going to take out this piece and make a total mess of it. So this is to replace r with u of r. So what I've done here for the second partial of r is I've taken the partial, not the derivative of u over r, which is going to be the second derivative. You see how I did that? Now, if this is a product again, so I have to take the product of these two. So, first of all, I'm going to take 1 over r times the derivative of u with respect to r minus r squared. What happened there? Well, the derivative of 1 over r, which is r to the minus 1, use the exponent, the minus comes out front, and the exponent goes more negative by 1. So it's r squared u. Now we're going to take the derivative of this mess. So we've got to take the derivative of this product minus the derivative of this product. So let's see how we do with that. Well, on this first round here, I'm taking the derivative of u with respect to r and taking the derivative of that. It gives me the second order derivative of u with respect to r, and the 1 over r comes along for the ride. Then, in the same way that I got this minus 1 over r squared, I'm going to take the minus 1 over r squared. Let's see, did I do that correctly? Oh, I've got to take 1 over r, which again gives me a 1 over r squared du over dr. Plus, I've got to do these two things. I'm going to take the derivative of this 1 over r squared, and that's going to give me a negative times a negative. This goes to 3, and then there's a 2 up here. So that's the exponent rule and all that kind of stuff. So you see a minus 2 comes out front, turns that into a positive, 2 goes up here, and we've got r3 down here times u. And then finally, I take du over dr, derivative of du over dr times negative r squared. So all of those terms come about. See how easy it is? It's so easy that I confuse myself when I try to explain it. Now let's take this line and see what we can do with it. Well, the final run here is no change here. This became a minus 2 over r. How did that happen? Well, they're 2 over r squared. Where there's 1 over r squared, 1 over r squared, they're both minus, So that becomes a minus 2 over r squared du over dr. And as you can see, this is going to cancel when we come to the next line here. Plus 2 over r cubed u. Once we get to the bottom here, we probably want to take a big break before we go on. At least I do need that. Now, what's this line? Oh, this is the green line. Now this one isn't that bad. 2 over r times the derivative of u with respect to u over r. Here's 2 over r already. And that came from up here in the green line. And then 2 over r, and we take that times all of this stuff, which is this stuff basically, which is 1 over r du over dr plus derivative of 1 over r, which, as we did before, gives me 1 over r squared. And if we multiply the 2 over r through, here's what happens, is the 2 over r multiplied through there times this 1 over r squared u becomes 2 over r cubed. And isn't that funny? That 2 over r cubed matches this 2 over r cubed. And this 2 over r squared du over dr will cancel out with this negative 2 over r du over dr. So we get rid of some stuff, and that magically got simpler rather than more complicated. So now we can come down here, and this is all that's left. All that's left out of this mess is h bar squared 1 over r the second derivative of u with respect to r, blank, all those things canceled out, minus the lambda over r cubed. Now how did that r cubed get there? Well, let's see where that became an r cubed. Oh, it's u over r, not just big R anymore, it's u over r, so that became an r cubed down there. And then we have minus e squared 4 pi e to the 0 r squared, and then this becomes e to the u over r. Well, I think you can see we got too many r's. So I'm going to multiply both sides by r, and here's what I get. Second partial here. Here's our lambda. It's going to help us talk about some things here. And this is going to be called something like a centrifugal something or other. And here's the potential energy. And anyway, I just wanted to derive that so that we can proceed with caution.